Whenever a carboxylic acid loses its OH group, the ic acid at the very end is replaced with OYL. I'll give you an example here. So here we have propanoic acid. Okay, and if it loses the OH group, then we have CH3, CH2, C, O, like that. And instead of calling it propanoic acid, okay, we were going to remove this part here, and it becomes propanoyl acid. Oh, not acid, sorry. Propanoyl group. A dicarboxylic acid contains two carboxyl groups, and they are named by adding the ending DIOIC acid to the alkane name. Okay, I'll give you a name or an example here. So here we have, whoops. Okay, we have two carboxyl groups. And here, the common name is oxalic. Okay, so that's the common name. The IUPAC name is going to be, so we have two carbons, right? So we have ethane, but instead of ethane, we're going to replace the ending, or no, we're going to keep the ending and just add the DIODIC to it. And then acid. Okay, so we keep the E from the alkane and just add the DIODIC to it. So, but again, most of these guys are known by their common names. Esters have the OR group attached to the carbonyl carbon atom, and esters are unable to hydrogen bond like carboxylic acids are. And that makes them have, and they have a lower boiling point than the carboxylic acids, right? Because there's not as strong interactions because there's no hydrogen bonding. Simple esters are volatile liquids, and they have pleasant odors. And it says they contribute to the natural fragrance of flowers and ripe fruits. When naming esters, the name consists of two words. The first name is the name of the alkyl group R in the ester. Let's do an example there. Okay, so I'm just going to use this one right here. Okay, so we're going to name the alkyl group that is in the R. So whatever this is going to be, we'll name that first. And the second name is the parent acid with ic acid being replaced with 8. Okay, so right here is what we're talking about. So this is from acetic acid. So acetic acid. So what we would do is we would take out the IC acid. So this portion here, we're going to remove that, and it becomes acetate. Okay, so we'll name the R first, whatever it's going to be, and then we end with acetate. So I'll give you an example of one of those. Okay. Here we have, draw this ring. Oh, I did not draw that right. Okay. Okay, so that's benzoic acid. Okay, and then we have our R group here. Okay, so we're going to name the R group first. So we're going to name this portion first. And it is, there's 4 carbons, so it's butane, but we're going to name it butyl. And then we name the carboxylic acid it came from, which was benzoic acid, but we're going to change the ic acid to ATE, so it becomes benzoate. Okay, and there's a list of the carboxylic acids in your book with the common names that will really help with all these. Okay, amides have a nitrogen group bonded to the carbonyl carbon atom. Amides are able to form hydrogen bonds like carboxylic acids are. Primary amides are able to form multiple hydrogen bonds, so they actually have higher boiling points than the carboxylic acids. The primary amide in the example has 2 hydrogens that are able to hydrogen bond with other amides. So, with carboxylic acids, they have that OH group, so they only have 1 hydrogen ion. But here, with the primary amide, there's 2 hydrogens able to form those hydrogen bonds between the molecules. So, it causes them to have stronger interactions and higher boiling points. Primary amides have lower molecular weights and are solids except for formamide. Can't say it. Which is a liquid. So most are solids except for that one is a liquid. They are soluble in water and organic solvents. So they're soluble in water because of that hydrogen bonding. Secondary amides can also form hydrogen bonds, but tertiary amides cannot because there is no hydrogen on a tertiary amide. So let me give you some examples here. Okay, so we have, here's an example of a primary amide. All right, so the nitrogen is bonded to the carbon and the carbonyl, and we have 2 hydrogens available for hydrogen bonding. Okay, so that's primary. Secondary would look something like this. So only 1 hydrogen available for bonding, but we still can do, hydrogen bonding there. And then a tertiary amide would look something like this, where there's no hydrogens available to form those hydrogen bonds. So only primary and secondary can form hydrogen bonds.